Hey Math 2B, this is Mr. Roberts, Shasta High School. I'm here just to offer some assistance with this particular set of practice problems. The first one says a regular polygon has an interior angle of 135 degrees. How many sides does it have? Determine the number of sides using two different strategies. Show all of your work. So if we're looking at this regular polygon here, they're telling us that one of these angles is 135. Now, obviously, this polygon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This has 12 sides, right? And that doesn't mean that the answer is 12. That just means, for example, I'm just trying to show you what we're talking about. One of the interior angles is 135. One of the strategies would be to use the fact that if we take the number of sides and subtract 2, multiply that by 180 and divide by the number of sides. That gives us the size of one of these angles. So we could just go ahead and say, hey, look, this expression right here is the sum. It's the measure of one of the internal angles of a regular polygon. And we could say, look, that's 135. Solve this for n, and then we'll know how many sides it has. So that's one strategy. Another strategy is to recall that if you were to construct an exterior angle, right, at each one of these vertices, we know that all of these exterior angles add up to a total of 360. So in other words, 360 divided by the number of sides equals some angle right here. Well, that angle is relatively easy to find because we know that the 135 and this angle have to add up to 180. So if you take this angle in the question mark, plug it here, it's pretty straightforward to solve this equation for n also. So anyways, how many sides does it have? You know that when you plug in n here, you should get 135, and also 360 divided by n should give you whatever this particular angle is. So that's the first problem. The next problem, by the way, it's not done. Those are just little assistants. The next problem it's kind of a review of our trig ratios, and they're starting with C. Not all the C's first, but there's the C's and some A's. So let's put ourselves at angle C, and they're saying, for example, the tangent of C is AB, and over here this is the length of AB. So if this is segment A to B, this represents its length, and BC represents the length of segment BC, and AC would represent the length of segment AC. So if we're here, yeah, the tangent is the opposite divided by the adjacent. So for sure, that's the tangent. Well, what's the sine of angle C? If I'm sitting here, what's the sine? Well, you can look up on the chart or recall or discuss it. Right? You know what the sine ratio is. And then for D, it says what's the cosine of C. So all of these ones that I'm circling, you're sitting here at angle C, and then they switch it up. They say, hey, what about angle A? So what are the tangent, cosine, and sine ratios if you're sitting here at this particular angle? So this is a very good model. It's showing you what your answers ought to look like. Let's see this diagram. It says examine the diagram at right. Given that two of these bigger triangles here are congruent. Which triangles? A to B to C. So this, let me do these in slightly different colors. Actually, I'll highlight them. One of them's A to B to C. That triangle is congruent to triangle E to D to F. So they're definitely overlapping each other, but they're congruent triangles. And then it says, hey, is this triangle right here in the middle isosceles? Well, you know, in order for this to be isosceles, right, there's this thing, if we could show that the base angles are the same, then yeah, it would have to be isosceles. And the other thing is to remember, if you look at this angle F to D to E, F to D to E, and angle C to B to A, those angles are in the same location of congruent triangles. Anytime you've got corresponding parts in a triangle that are congruent, those angles are congruent. So you can easily point out that, hey, this angle right here name it, is congruent to this angle. Why? Because they're parts of the green and the yellow triangles, right, that are congruent to each other. And if you have a triangle in which these base angles are congruent, then you know that the sides across from them have to be congruent. And if these sides are congruent, then by definition this is isosceles. So it's not a difficult looking proof, and I'm not going to spell out all the parts for you, but the big thing is hey, you've got congruent triangles. You know what those are. Put that in the box and say that that's given. Because those triangles are congruent, there are some angles that are congruent, right? And it's basically like, hey, if you got congruent triangles, then we've got congruent parts. That's a reason for that. And we're talking about this angle and this angle. Now that we've got that, we can say, oh, those are the base angles of that triangle. So now we can claim that we've got some congruent sides, right? The congruent sides we can claim, we would talk about this side right here being congruent to this side. And then finally, since those sides are congruent, we can say, hey, this triangle is isosceles, and the reason is its definition. So anyways, that's an idea, and I think perhaps you might be able to create kind of an organized proof from that chicken scratch. I know the fact that these have the I in them seems like they're a little bit more mysterious, but just remember it's just the imaginary index, and remember when we see I squared, we know that that equals -1. And for each of these, right, you can use a generic area model. I don't think you actually need to for these problems, but if we look at D, we're multiplying A plus BI times A minus BI. And if I do the multiplication here, this is clearly A squared. This is A times B times I. This is negative, and I'll rearrange the terms, A times B times I. And down here I've got negative B squared I squared. Well, these are absolute opposites, so they totally cancel each other out, right? Those are gone. A plus B, or negative ABI and plus ABI is just going to equal 0. And what remains is A squared minus B squared I squared, except we know that this one part of it is equal to a -1. So if you just go ahead and multiply this negative B squared times a -1, it changes the final answer. So make sure you get that right. And then definitely you can do A, B, and C. Similar technique on all of those. Jamil solves the quadratic equation x squared plus 3x minus 10 equals 8, and her work is shown below. When she checks those solutions, though, they're not working. They don't make the equation true. But she can't find her mistake. Can you explain her error? And if I was to put in just one of her answers, right, like for example, if we put in the number 10 into that original equation, that becomes 10 squared plus 3 times 10, which is 30, minus 10, and that should equal the number 8, right? It should be that, but this becomes 100 plus 30 minus 10, which is 120. That's clearly not equal to 8, right? So obviously these are not the solutions. Why not? Well, the thinking here, whenever we get to a point where we're setting these factors, right, this particular factor and this particular factor, we end up setting them equal to 0 because we're using something called the zero product property. Remember, if we multiply two values, A times B, and we get an answer of 0, then either A is 0, so A is 0, so we set this first part equal to 0 and solve, or it's the case that B is equal to 0, so we set the second part equal to 0 and solve. Well, that works if this is the number 0, but if it's the number 8, you can't assume that if you're multiplying two things, you get an answer of 8. This would be like saying, hey, A times B equals 8. Okay, that means either A is 8 or B is 8. No, it doesn't have to be. I mean, um, A could be 2 and B could be 4, right? Or you could have that this is a 4 and this is a 2, or you can have that this is a 1 and an 8, right? There's a lot of different ways that we can get the number 8 out of those products. We can't use any of those to solve this equation for x. The zero product property works because it's a special number, right? It's the only place where this works. If you're multiplying two values and you get an answer of 0, either this has to be 0 or this has to be 0. There's no other way around it. One of those two is 0. And we get our two solutions by letting each one take a turn being a 0. So I want you to try and solve this now. Probably a better thing to do would be to subtract 8 from each side first, and then attempt to factor. If factoring doesn't work, you might want to create a space and complete the square, but those are two different tactics. And if all else fails, of course, there's the quadratic formula you could run to. I love this question because it's kind of instructive. It says one way to look at absolute value is to think of the absolute value of a number as its distance from 0 on the number line. For example, the absolute value of 6 is 6, and the absolute value of negative 6 is 6 because both 6 and negative 6 are exactly 6 units from 0 on the number line. You can therefore think of an equation as x, what is this? The absolute value of x equals 5 as the question, what numbers are exactly 5 units from 0 on the number line? That's why whenever we drop the absolute value symbol, we always introduce this plus and this minus. Now this says draw a number line to show the solutions to the following equations. Well, I don't know how involved this should be, but look how quick this is. For A, I drew a number line, and I'm looking for two numbers that are 3 units away from 0, right? And the two spots that are 3 units away from 0 are at positive 3, so this is a solution here, and the other one is at negative 3, so this is a solution right here. So go ahead and try to do that. One of the things you might want to do is before you sketch it like this, get the absolute value portion of your equation by itself. So, and what I mean by that is this absolute value portion right here, that should be isolated first. Now you can see in the first two problems it is already alone, so it's pretty easy to sketch the location of those two solutions. But for a problem like, for example, this one right here, you should get the absolute value alone first by subtracting 2 from both sides. And to get the absolute value alone here, you should divide both sides by 3 before proceeding to try and sketch this. And I really want you to think about E and F, right? I'm eager to see what you come up with, but what are the values of x that makes those equations true?